It is Tuesday, October 27th, 2020. Today we're going to be talking about normal distributions / curves again. As we jumped into a little bit on Thursday, we're going to be looking at how to draw normal curves, and we're going to look at the 68, 95, 99.7 rule. So here we go. All right, the normal distribution. We got a brief introduction to this on Thursday. All right, the mean. This letter is mu, the Greek letter. And the standard deviation sigma completely determine the shape of a normal curve. If I have those two values, I can draw the normal curve for that distribution, if it's a normal distribution. Mu can be easily seen as the center of the peak of the curve. Sigma, or the distance from the center of one standard deviation, can be seen in the curve as the points at which the change of curvature on a normal curve takes place. This is only true for normal distributions. These things are only true for something that we know is a normal distribution, or we've been told is a normal distribution. Skewed distributions, this is not the case. Or even some symmetric distributions, this is not the case. Right. And so then our formal definition, which kind of repeats some of the things on the previous slide, for the normal distribution and normal curve, we have a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean, mu, and standard deviation, sigma. The mean of a normal is at the center of the symmetric normal curve. Standard deviation is the distance from the center of the change of curvature points on either side. The change of curvature points just refers to, as we trace along the normal curve, it's kind of like how when the steepness of the curve changes. The really important thing here is a new notation. We abbreviate the normal distribution with mean, mu, standard deviation, sigma, as n, parentheses, mu, comma, sigma, parentheses. So we have this new notation that when you see this, it means that we have a normal distribution with a mean at mu and a standard deviation of sigma. So this is the important, new piece of information we're getting from this definition that we haven't kind of seen already. If you're writing this down, can you please raise your hand to say that you need more time? Good. I don't see any hands. All right. Why is the normal distribution important? Why do we care? They're good descriptors for some distributions of real-life data. Right? They model real-life situations and things that actually happen. It's not just like a theoretical thing. A couple things that fall into things that are approximately normal. We have scores on by many people, like the SAT or IQ tests. If we look at the distribution of those scores, they fall into an approximately normal distribution, that bell curve. If we have repeated careful measurements of the same quantity, like the diameter of a tennis ball, for example. Right? So at a factory, they're going to measure the diameter of tennis balls to make sure they're all about the same. There's an acceptable variance in the diameters. Right? Everything kind of falls within that range. And within that range, there's a normal distribution of the diameters. Characteristics of biological populations, such as lengths of crickets or yields of corn. Right? Once again, there's kind of the typical range for these sets of data. And along that range, it's approximately normal. Okay. Normal distributions provide a good approximation to the results of many chance outcomes. So this starts introducing the idea of probability and chance, okay, such as the number of heads in many tosses of a fair coin. So if I were to have everyone in class take a coin and flip it 20 times and record just the number of heads that show up when they flip the coin, and we plotted all those numbers on a histogram or a dot plot, we would get something that's approximately normal. It helps represent the number of heads, right, in this chance situation. Right? And then this is a key thing that we're going to use later on in the class. Many statistical inference procedures are based on normal distributions. Right? So how we make inferences is influenced by normal distributions. Can you raise your hand if you need a moment to write any of this down? Now, how do we draw a normal curve? There is a process. There are 6 steps. Not as bad as you might think. Number 1, draw a number line with 7 evenly spaced tick marks. Label the one in the middle with the value of mu, and those to each side with mu plus or minus sigma, mu plus or minus 2 sigma, and mu plus or minus 3 sigma. Draw a dot above the mean value where the peak of the curve will be. The height of this dot just depends on the spread of your data. So like for something that has a really high standard deviation, like a large number for the standard deviation, it's more spread out. That means the peak is going to be shorter. Something with a small standard deviation is going to be more narrow. The peak is going to be higher. Above the marks, 1 standard deviation from the mean, draw dots about 60% as high as the dot above the mean. Above the marks, 2 standard deviations from the mean, draw dots about 15% as high as the dot above the mean, or about a quarter as high as the dots above 1 standard deviation. Step 5, above the marks, 3 standard deviations from the mean, draw dots just above the horizontal axis. And lastly, connect the 7 dots with a smooth curve. So these are our steps for drawing a normal curve. Right. If you need another moment to write these down, please raise your hand. So let's draw one. Alrighty. So we're going to start by drawing a straight line for the number line. Good enough? All right. And then in the middle of our line, tick mark. This will be mu, our mean. We will space evenly as we can. 3 tick marks to the right. 3 to the left. Seem pretty close. All right. So then, moving to the right of the mean, we have mu plus sigma, whatever our standard deviation is, added to mu. Mu plus 2 sigma. Right, 2 standard deviations added to the mean. And then mu plus 3 sigma. Right, 3 standard deviations above the mean. And we repeat the same thing except subtracting. Mu minus sigma. Mu minus 2 sigma. Mu minus 3 sigma. All right. So now we have labeled our general graph here appropriately. As far as our number line goes. Right, and this is based on being provided the fact that we have a normal distribution with a mean of mu, standard deviation of sigma. Now, we're going to go directly above mu, put a point. Right, in this case, it's not super important how tall it is. We're just doing a general case. We don't have a number. This is just we're demonstrating the process on how to draw it. Now, 1 standard deviation from the mean, I need to go to about 60% the height of my first dot. So about like halfway and then a little bit more. See there. All right, and then we go directly across to 1 standard deviation less than the mean. We get our other dot. Then we go 2 standard deviations, and this is 15% of the original, or a quarter of the height of the second dot here. Okay, so like halfway is about here, quarter is going to be about here. Now it's not going to be perfect, right? Because I don't have like grid lines. Like that. I'm just eyeballing this here. Right. And my other dots, you can definitely see that my spacing is not uniform. Our last dot here just goes slightly above the horizontal axis. And now we have all of our dots, which now means I can draw my curve. So we'll start over here. Start kind of like here and we'll slowly curve up. And we'll curve up a little faster. Close. Again, it's not perfect. Artistry is not my strong suit, but we can see the general idea. All right, and so this is kind of how we can sketch out a normal curve if we're given the mean and standard deviation. We just use the same process with numbers. We just write numbers here instead. Like we could have, 5 and 1. And then this would just be 5, 6, 7, 8, 4, 3, 2. We just replace our estimates, right? The mu and sigmas with the actual values. Any questions? All right. Anyone need a moment to draw any of this if they're taking notes? All right, so this leads us to our 68, 95, 99.7 rule. But before we see exactly what this is, let's consider an example from previous class. All right, last week we saw a distribution of ITBS vocabulary scores is symmetric, single-peaked, and bell-shaped. This was the graphs that one of the graphs that I used when I introduced the normal curve. Right? Suppose the distribution of scores is exactly normal, with mean mu equals 6.84, right here in the middle, and standard deviation sigma equals 1.55. Figure to the right shows the normal density curve for the distribution with the points 1, 2, and 3 standard deviations from the mean. So along the bottom, I have the actual number values. And along the top here, I have how many standard deviations to the right or to the left those numbers are. It creates this kind of like gridded area for us to use. Anything else to point out? If we look at the size of this, right, this would be 1.55. Right? It's the same here, right, from here to here. It's representing the same amount of units. Right, so the width between each of these standard deviations has to be the same. All right. Now, this gets us extra information now that we have this kind of like normal curve, this equal spacing. We get more data. Right? The 68, 95, 99.7 rule. Right? In a normal distribution with mean mu, standard deviation sigma, approximately 68% of the observations fall within sigma of the mean, one standard deviation of the mean. And that's in this illustration here. This middle area represents 68% of our data. And this is just a known thing. If you have a normal distribution, 68% of your data will lie between, or approximately 68%. It might be plus or minus the decimal portion of a percentage. But approximately 68% of the data is between one standard deviation of the mean. We then move out a standard deviation to 2 standard deviations, and we are at approximately 95% of the observations fall within 2 standard deviations of the mean. Okay, so we're now looking at the -2 to the +2. The area under the curve between those points is 95% of our data lies in that area. We go to the 3rd standard deviation. We're at approximately 99.7% of the observations are within 3 standard deviations of the mean. So we're at these last bars here from -3 to 3. Between those bars, 99.7% of my data lives there, which means there's 0.3% that's outside of those bars. All right. So the other stuff we can add to this is we can break down the percentages even more if we want. That is to say that, you know, between 1 and 2 standard deviations here, this shaded area represents, I think it's 13.5%, right? And this has the same amount. It's evenly split up. Right? I could go even further, right? If this is 95%, this is 99.7% in the next stage. That means that between the 2nd and 3rd standard deviation on each side, we'd have 4.7 divided by 2. 2.35%. I can break this all down so that each chunk represents a certain percentage, right? And then we get, you know, from here over everything. right, and everything else to this side. This would be 0.15%. Now notice we have symmetry. There's the same percentage in each section as we move out. Right, so please keep that in mind. There is symmetry in the normal distribution. Any questions? Does anyone need another moment to write any of this down? All right. Let's look at an example. So we want to know here, we have our same distribution we've been looking at, the ITBS vocab scores, and we have our normal distribution with a mu 6.84, the mean. Standard deviation is 1.55. We want to know what percent of the ITBS vocab scores are less than 3.74. So we'll go over to our graph here. 3.74 is right here. So I want to know what's the proportion of my graph that's over here. What does this represent, percentage-wise, of my data? Okay. So what we know, oopsie-daisy, sorry, is that between these 2 points lives 95% of my data, right? Between two standard deviations. And I'm looking at one side of the graph that is outside of that, right? So beyond the 95%, I have 5% left. Since we have symmetry, half of that 5% lives on this left-hand side that represents less than 3.74. And the other half lives over here. So that means this proportion to the left of 3.74 is 2.5%. Right, that's this entire green portion. Right? Okay. And we can kind of figure this, like if we're asked to show our work in some situation, we would have 100% minus 95% that we know is not included. That's not the area I'm looking at. And we only need half of that leftover space because we're only looking at half of what is left after taking away the 95%. So we divide by 2. The 5% divided by 2 equals 2.5%. So 2.5% of the ITBS vocab scores are less than 3.74. Any questions on question number 1 or example number 1? All right. Okay. So then the next question is, what percent of the scores are between 5.29 right over here and 9.94? So now I'm not looking at this entire 95% or just a section of something else. I'm looking at like the middle section plus another chunk. Right, so I'm looking at 68% plus this other section. Okay, so I need to know what this section, what percentage is this section. And we already saw this in this one. Right? The percentage of this other section is 13.5%. Right? But how do we get that? Right? And how we kind of figure this out mathematically is we know that we have 95% between the two standard deviations, but I only need half of that to add to my 68%. I'm going to say 95 minus 68%, because I want to know what's the proportion that's just from one standard deviation to the second standard deviation. Divide that by 2. Get 27% divided by 2. And that gets me that 13.5%. And then we add that to the 68. And that gets us 81.5%. So we have 81.5% of the scores are between 5.29 and 9.94. Right? So there's a lot of value we can get out of the 68, 95, 99.7 rule because it allows us to kind of like chunk out this whole thing and know what percentages or what percentiles things fall into. What questions do you have, or what can I clarify, or what would you like to see again? Okay, so I'm going to do a quick look into this week's module. Right, it is week 10. We have the module mostly built out here. We're in section 2.2. We'll remain in section 2.2 later this week. We have our live class resources. Right, the notes and the recording of the lesson will be uploaded once they are ready. There's a couple of AP Daily videos that have to do with the normal distribution and how to use them. We're also in these pages of the textbook so far in section 2.2. We got the digital book right here in the resources. Then we have a discussion board for today. It is the 68, 95, 99.7 rule discussion board. Essentially, it is a problem very similar to what I just did in the example with the ITBS scores. This is having to do with height. So you'll need to essentially do a lot of what we just did. All right. The other discussion board I haven't opened up yet because we haven't talked about how to use table A yet. That's something that I need to go over before we can do this. And I'm kind of still deciding what I want to do for the CYU this week. For like the weekly evaluation. So I'm kind of figuring that out still. So once that's ready, I'll have it available. All right. So, any questions about the week?